So in this video, we'll be picking up from where we left off in the last video. So we'll be talking about how we can use the Arrhenius equation in a couple of ways to get some useful information. The main way that we'll be using the Arrhenius equation is actually to find the activation energy of a reaction. Okay, so just a quick refresher about the Arrhenius equation. So the Arrhenius equation tells us how our activation energy, our E sub A, is related to the rate constants, the K values that we've been working with a lot in class. All right, so this is our rate constant. And it does this through this equation here, all right, where our E sub A is our activation energy. That's that energy difference between the reactants and the transition state or activated complex. K is our rate constant. R is our gas constant. Typically, that's going to be 8.314 joules per mole Kelvin, but just be careful with your units here, because that might not always be the case. Typically, what you're going to see is that whatever units your gas constant is in is also the units that your activation energy has to be in. And that's just how the unit math works out. So just be very careful with your units when it comes to thinking about your gas constant and your activation energy. All right, so that's K, E sub A, R. T is our temperature in Kelvin, and then A is that frequency factor, which reports on how likely is it that a collision with the proper orientation required for the reaction will actually occur. Right? So let's look at a couple of key points about the Arrhenius equation that I wanted to summarize. So mostly this is just, what does this mean? So what this means is that the Arrhenius equation tells us that fast reactions occur when reactants collide in the proper orientation frequently. So that's that high A value. They also occur when temperature is high and when activation energy is low. All right, so another way to think about activation energy, is to think about it as an activation barrier. Because you need to be able to reach that activation energy in order for the reaction to proceed. So it's acting as the barrier that prevents reactions from occurring most of the time. So you can imagine that if that barrier is low, if you have a low activation energy, it's going to be a lot easier to just hop over it and have your reaction occur. Right? So more molecules will be able to react if the activation energy is low. So that's why when your activation energy is low, typically the reactions are faster, right? But let's focus for this video on this temperature piece. This is really important because temperature is measurable. And what's also measurable is our rate constant. Can also determine K from experiments. All right? And something about K is that this value we've talked about is specific to a specific reaction. It's also specific to a particular temperature. So if you change K, or if you change T, you're also going to be changing K. All right? Change T, change K. And why this is useful is that we can use that knowledge, we can collect a bunch of experiments, and then use the Arrhenius equation to determine the activation energy. And the most common way that we do that is through the linear version of the Arrhenius equation, which I've shown here. All right, most commonly you're going to be working with this form of the equation. But how did I get from point A to point B? So to get from this form of the equation to this form of the equation, we have to use some of our log math. And so the first thing that we're going to do is we're going to take the natural log of each side of the equation. And that brings us to our first log rule. So the natural log of a product is the same as the natural log of one of the things that you're multiplying plus the natural log of the other thing that you're multiplying. So we can rewrite this as natural log of A plus the natural log of all of this. And this is useful because we have another log rule. So it turns out that when you take the natural log of e to the n, that just equals n. So this is a way for us to remove this exponential term, which makes it a lot easier to look at our activation energy term. So now we have our natural log of A plus our activation energy over our gas constant times temperature, which we can rewrite just to make things a little bit clearer. Like this. So I just pulled that 1 over temperature out of this term, okay? Just to make it a little bit clearer for looking at this equation. And this equation is the same as what I wrote down here. It's just rearranged a little bit to make it easier to look at. And so the reason why we did that is because this is very similar to what we did with the integrated rate laws. So now we have something that looks like y equals mx plus b. So this equation makes a line, right? And that's really useful because it tells us that we can make a graph with the natural log of our rate constant on y and 1 over our temperature on x. Just a rule of thumb is that whatever you're changing goes on x. So we can directly change the temperature, so that's what's going to go on the x-axis. And so when we make this graph of natural log of our rate constant on y and 1 over t on x, we end up with a line, and the slope of that line is equal to the negative of our activation energy. So just whatever our slope is, our activation energy has the opposite sign. So in this case, our slope is negative, so our activation energy would be positive over r. But we know r, that's constant. So from the slope of this line, we can determine our activation energy. Very useful because usually we don't know our activation energy. We can also determine our frequency factor from our y-intercept, okay? So from this one graph, we're getting both our activation energy and our frequency factor. This is a very common, very useful experiment that's done a lot in the lab. But the thing about this version of the equation is that in order to get a reliable slope, you need to have a lot of different experiments at different temperatures. So you kind of need to collect a lot of data for this, and also you need to be able to graph the data, which we're typically not going to be able to do on an exam. So we can do something a little bit more useful where we use a 2-point version of the equation, and that is shown here. So what do I mean by 2-point? I mean that we're going to look at 2 temperatures and only those 2 temperatures. Right, and this is where that K being temperature dependent comes in. So if we have 2 temperatures and we know both Ks, both of our rate constants, then we can find the activation energy. All right, just by substituting in our temperatures and our rate constants. Another way that we can use this equation is if we know our activation energy and we know our temperatures, and we know one of our rate constants, then we can find the other rate constant. So this equation is useful in a couple of ways. Typically, we're going to be looking at finding our activation energy, though. Okay. So let's try a practice problem. What types of questions might we see when we're looking at the Arrhenius equation? So let's work through this problem. So this is telling us that the rate constant for the rate of decomposition of dinitrogen pentoxide to nitric oxide and molecular oxygen is 1.66 at 650 K. All right, so we have a rate constant is 1.66 liter mole seconds, and that temperature is 650 Kelvin. All right, and it also tells us that, okay, so the rate constant is that at that temperature, and it's this value at this temperature. So we have another K, so I'm going to call that K2, 7.39 liters per mole seconds. And our second temperature is going to be 700 Kelvin. And then it's asking us to calculate the activation energy for this decomposition. All right, so EA is unknown. So looking at this information that we have, we can tell that we need to use the 2-point version of the Arrhenius equation. All right, so I'm just going to write that out here. All right, and so we know everything that we need to know, because we know R is just going to be 8.314 joules per mole Kelvin. Just be aware that that means that our activation energy is going to be in joules per mole. Those are the units that you should end up with. So now we can just plug our numbers in. So natural log of 1.66 liters mole seconds over 7.39 liters per mole per second is equal to our activation energy over 8.314 joules per mole Kelvin times 1 over T2, so that's 700 Kelvin, minus 1 over our T1, which was 650 Kelvin. Right, so I'm going to kind of do a couple of calculations at once in each of these steps. So first, one thing we can notice is that these units are going to cancel. So we don't need to worry about those units anymore. So now that becomes this this stays the same. This becomes 0.0014 Kelvin minus 0.0015 Kelvin. Right, so natural log and then this becomes, I'm going to switch to scientific notation. Those are 1/kelvins, not just kelvins. Right. So then we're going to divide both sides by this, and that we're going to end up with 13589 is equal to our activation energy over our gas constant. And this units here are Kelvin. So then now we're going to multiply both sides by gas constant, joules per mole Kelvin. Kelvins are going to cancel, and so we're left with, this cancels out, our activation energy is equal to 113,000 joules per mole. All right, so that is an example of how we can use the Arrhenius equation to find the activation energy. All right, and I'll have more practice problems in your guided notes assignment. So that concludes the video on practical uses of the Arrhenius equation. Next time we will pick up with reaction mechanisms. So this is asking like what exactly is happening when our reactions are occurring and what event is actually controlling the reaction rate. So that is where we will pick up next time, and